Well, good morning, everyone. As a geologist and a paleontologist by training, I'm very interested in history, deep history. And so it's with great pleasure that I'm with a group of historians. I know that you're gardeners as well, but historians surely foremost. All right, this first slide is, would you believe, of a fossil fish. And I love this image. The fish is about 1 million years old, collected from old lake sediments and a road cutting inland of Gisborne on the coast of the east coast of the North Island. Hang on, that's one. But I should point out, go back. No, I can't go back. There we go. For all that it is a fossil fish, everyone, it is not the fish we're talking about today. It is, in fact, the crag. All right? So it's a lovely metaphor for New Zealand. So you can think of New Zealand as a fish, and here is this spectacular crack, which is the plate boundary. And in order to understand, if you like, the history of New Zealand's landforms or landform, we need to understand the big picture, and that's what I'm going to talk about largely today. In a nutshell, the Pacific plate is moving westwards, and the Australian plate is moving northwards, and you end up with a sum vector, everyone, oriented like that. So that, in a nutshell, that explains the shape of New Zealand. But this is a very powerful diagram in many ways, even though it's actually pretty simple. It's very important to understand that the Pacific plate's moving at about 5 centimeters a year in this direction. And down here, guess what? The Australian plate is moving in this direction now, from west to east, at about 3.5 centimeters. And this is a geological convention. See the ticks? That denotes the direction of subduction, the process whereby one chunk of the Earth's crust goes under another. And note the orientation that ticks on this side. It's the opposite. And in between, no ticks. So I'm going to explain, I hope, what's going on. And just in case we don't get there, because I've only got 30 minutes, here are my conclusions. And I've written them in great detail, but the important thing to note is that our history is essentially the product of our geological inheritance. Our landform is the product of our geological inheritance. And I think of our history in terms of 3 phases. Our Gondwana history. We were on the edge of Gondwana for 425 million years. And then our Zealandian history. Zealandia broke away with formation of the Tasman Sea, and that occurred between 85 and 25 million. So we have a Zealandian history. And then our New Zealand history, which I think of as the last 20 million years. And in terms of subduction, and this is a really important part of New Zealand's history, with respect to Gondwana, we had cessation of subduction 105 million years ago. And then resumption of subduction 25 million years ago. And this will become a bit clearer with the talk. I now think of New Zealand, everyone, in terms of 2 ocean-forming processes. Our history relates to the opening of the Tasman Sea between 85 and 55 million. That just took 30 million years to happen. And we've been frozen ever since with respect to Australia. And then the opening of the Great Southern Ocean from 35 million years ago to the present day, and that's still happening. And lastly, most importantly, our topography and our soils are the result of processes at different scales, but I put it quite simply this way: you can think in terms of processes at the mantle scale, hundreds to thousands of kilometers in wavelength. Our crustal scale, our crust is actually quite thin, so between 10 and 30 kilometers. And things happening on the surface, subject to rain, wind, sea, climate, giving rise to everything we see at the surface: rivers, plains, gravels, And I mentioned dunes, loess, windblown sediment relating to the last ice ages, our coasts, glaciers, and then, of course, seismic shaking, landslides, tsunami, weather. Those are the natural hazards that impact. Those are the conclusions, everyone. And now we'll proceed and we'll get there in the end. And I'll start with a lovely image that some of you will be familiar with. This is a scene down in the South Island, the Hector Mountains here, and this is Lake Wakatipu, and we're looking north, and in the distance is Queenstown up there. So some of you may have been there. It's a beautiful landscape, and I've chosen this mainly because it's glacial topography. This lake is only 17,000 years old. Prior to that, it was choked with glacial ice. I mentioned Hector and the Hector Mountains. Here we are in Queenstown, and look at these lovely trees. These were actually sent as seedlings by Sir James Hector from Wellinngton to Queenstown, and there they are, pride of place, still growing. He died in 1907, I think. And here is James Hector, and I mention him for a number of reasons. He's founder of the Wellington Botanic Gardens, 1868. He's founding director of the New Zealand Geological Survey, 1865. And I'm a geologist. I worked with the New Zealand Geological Survey, which then became GNS Science. That's what this is. But most importantly, he was the founding director of this museum. And this museum opened its doors as the Colonial Museum in early December 1865. How about that? Here he is in 1868, by the way, and this is his marriage. I mentioned it, 1868. He opened the Wellington Botanical Gardens really as from a scientific perspective. He regarded it as a place where he could experiment to determine what sorts of plants from Europe and from North America in particular would suit New Zealand best. So he introduced a vast array of conifers. And by the way, in passing, here is Maria Georgiana, his wife, and her brother, lo and behold, Charles Munro. He's the very man who introduced rugby to New Zealand. I won't say any more about the rugby. All right, at last, an outline of the talk. And we're already halfway through. Let's move on to Zealandia. Have you heard of Zealandia? There it is. It's a very sympathetic projection, everyone. This is a continent. And look how small Australia is. I'll move on quickly. This is a map showing just water depth, but this highlights, this is gravity data, by the way, this highlights the extent of shallow water all around the New Zealand region. And this map dates from 2002. When this map came out, we Kiwis really sat up and thought, wow, what is all that shallow stuff? It had been known about for a long time, of course. I'll just point out New Caledonia up here, part of northernmost Zealandia, the Chatham Islands, eastern Zealandia. Zealandia was named by this man, Bruce Lyondike. He was working in Antarctica. He's an American from Santa Barbara, and he needed a name for a chunk of continental crust. So he gave Zealandia the name in 1995, and it stuck. We Kiwi geologists like the name. And by the way, he named it after New Zealand, but New Zealand was named by this man, Johann Blaau, not Tasman. So this is Blaau. He was a cartographer and probably the greatest cartographer of his era, based in Amsterdam. And I had the opportunity to get to Amsterdam this year, and here is the building in which he coined the term New Zealand. I reckon I got within 50 to 100 meters of the actual room in which he did that. He worked out that Tasman, who named New Zealand Statenland, was incorrect. Statenland existed elsewhere. So he named it. And that building's part of the University of Amsterdam, by the way. So this is Zealandia, and let me point out that it gets very close to the Australian continent. This is the Cato Trough, C-A-T-O, but it's separated by 25 kilometers of oceanic crust. And so too in the Red Sea, Africa separated from Eurasia. This continent is 95% submerged. It's 20 to 35 kilometers thick in terms of continental crust. It's more than 5 million square kilometers, surrounded by oceanic crust. And you can say it's the world's wettest, thinnest, smallest, third youngest, seventh continent. And the youngest continents I regard as Antarctica and Australia. Now, in 2017, a group of us published this paper in this magazine, GSA Today, and boy, did it draw a lot of attention, especially initially from the Australian media. They picked this story up and they said, wow, there's a continent just off the east coast of New Zealand and nobody's told us before. So this news was swept through Australia and then to the States and then on through Europe and Asia. And it was a fascinating experience. Look at that, reached an audience of more than almost 1 billion people, and more than 16,000 news agencies picked that story up. In this paper, the most contentious thing is that we redefined the word continent. So a continent, ladies and gentlemen, we could not find a scientific definition, but to us, and we enunciated it in this paper, a continent is a large tract of continental crust that is surrounded by oceanic crust and exceeds 1 million square kilometers. So that's what this is about. So this is Zealandia today, and I consider this to be the 7th continent if you regard Europe and Asia as one, and we geologists do. So that's Zealandia. So what's this thing about continental crust and oceanic crust? Let me explain. I'll gloss over this quickly. Very crudely, think of continental crust as granite and oceanic crust as basalt. So if you go to the moon and look back at the Earth and strip off all air, life, soil, water, you'd end up with a naked Earth, and it would reflect like the moon. It would be patches of bright white, which would be essentially granite, continental crust, and patches of silvery grey, basalt, like the moon. So when we look at the full moon, that near as damn it, that's the nearest we get to looking at what the naked Earth would look like. And basalt and granite are igneous rocks. They start off hot, and they vary as a function of composition, and hence they vary in density. So guess what? This is a density game. Continental crust is essentially floating with respect to oceanic crust. And I like this diagram. It highlights, in a nutshell here, percentage of Earth's surface at specific heights. So this is sea level. And what's interesting is that oceanic crust, on average, rests at the height on this planet is 4,500 meters below sea level, whereas continental crust is 450 meters above sea level. So that's a 5,000 meter differential, everyone. And I mention this because it's important in understanding how it is that we have something called subduction. How is it possible that solid rock can slide under another solid rock? So it's all about buoyancy. Zealandia broke away along this blue line with formation of the Tasman Sea. So this is Gondwana, and we split along this length, and this was what would become New Zealand, and that's New Caledonia. And this snapshot is at 90 million years ago. And New Zealand, or Zealandia, was moved through time along the bottom axis and through space in this way. And here, between 85 and 55 million, we have the opening of the Tasman Sea, and then later on, from 35 million on, the opening of the Great Southern Ocean. So you can see through time, New Zealand has traveled in the last 140 million years from latitudes close to the South Pole to its present location. And this is present situation, everyone. So Zealandia, Australia, Antarctica, and this is the modern rift operating between Australia and Zealandia and Antarctica. So it's a very interesting situation. So Australia and Zealandia are being pushed northwards as we speak, as a function of this rift. So that's it. That's Zealandia and the modern plate boundary, and you can now think of a northern Zealandia and a southern Zealandia. And the rates of those processes are well known from GPS. So this is the geologist's Earth. Plates are made up of a proportion of oceanic crust and a proportion of continental crust. And they reflect processes happening within the mantle. So think of the Earth's surface as just the skin. And the radius of the planet's 6,500 kilometers. Oceanic crust is no more than 7 kilometers thick, so oceanic crust is tissue thin with respect to the planet. And continental crust gets up to, well, in Australia it's about 40 to 50 kilometers thick. In New Zealand, Zealandia, it's about 20 to 30 kilometers thick, and that's why Zealandia is largely underwater. Okay, very quickly, we've got about 3 minutes to look at landforms. And I'll repeat this diagram. It shows what's going on, and we're going to look at Taranaki. We're going to be visiting the middle of the North Island. And I'll just point out that we do have a lot of earthquakes. This is a 10-year record. Shallow earthquakes, less than 40 kilometers. Deep earthquakes, greater than 40. And this image encapsulates about 20,000 about 200,000 earthquakes. We record instrumentally about 20,000 earthquakes a year, of which between 3 and 6 are magnitude 6 or greater. We get a magnitude 7 or greater about once a decade, and a magnitude 8 or greater about once every century. And this is what's going on. Let's home in on the local Wellinngton patch. We've got subduction, whereby oceanic crust on the Pacific plate is sliding under continental crust on the Australian plate. This is Pacific plate, that's the Australian plate. And the descent is about 12 degrees off the horizontal. And guess what? Beneath Wellinngton, in this region, the plate interface is actually stuck. And we are quite concerned about this. The rate of collision, as I say, about 5 centimeters per year. We've been using GPS since 1994, so 25 years of strain, 5 centimeters a year. That's 1.25 meters of accumulated strain. So at some stage, this interface here will fail with a very large earthquake. So we're now anticipating that. So I suggest that you just stay here for a few days. We'll zoom in quickly on this part of the world. So there's Mount Taranaki, Wellington's here, Cook Strait, the Marlborough Sounds. And what I want to point out is that this is a very interesting feature. This is just one part of New Zealand, and it's actually been drawn down as a function of lithospheric sag. So the downgoing plate is sucking down the overriding Australian plate, and it's drowning the topography above, like this. There's a lot going on in this country, I tell you. And I'll point out, here's the Wellington Fault, and we're very near it. Here's Wellington. And there's the Wairarapa Fault. And there it is, beautiful. Look at that, clear as a bell. It last moved between 300 and 500 years ago, and we don't anticipate it moving while you're here. It moves on average every 800 to 900 years. And this is the Wairarapa Fault, which last erupted in 1855. And I think you're going to the Wairarapa, and you will come down a road here, and this is Featherston, that's the railway line. It's about 60 kilometres from Wellington, and you'll bear in mind that you will cross the fault scarp here. This was the largest on-land fault displacement we know of, we humanity know of, in historic times, on land. It moved 13 metres sideways and 6.5 metres vertically in less than a minute on January the 23rd, 1855. Look at that, this cracking fault ripping through the landscape in Hawke's Bay. like a knife cut. Briefly, let's look at some volcanoes. That's Mount Taranaki. I mentioned this because it last erupted about 1755, but this is responsible for fertilizing much of eastern and central New Zealand. So the Waikato is fertile because of ash from this fabulous volcano. Here's Mount Narahau, which erupted in 1974, and that's Mount Narahau there, that's Ruapehu, so we're looking southwest, and this is Tongariro, and this is actually puffing away as we speak. And the last eruption of Ruapehu was 95 to 96. Fantastic. Quite different from this sort of volcano. This is Lake Taupo, which is considered to be one of the most dangerous volcanoes on Earth. They are so explosive, these supervolcanoes, that they never produce a mountain. They just produce a hole in the Earth's crust. This last erupted from around this part of the lake. We're looking, that's Taupo's up here. This is Turangi. So this is the east side, west side, New Zealand's largest lake. And it just forms a huge caldera. And when it last erupted in AD 233, here's Taupo. This is where the ash went, out in this direction. And everything, this is the footprint of the eruption column. Everything in here was completely destroyed. So all the bush in here is no older than 1,700 years. On average, this volcano erupts every 900 years, and it last erupted almost 1,800 years ago. Another reason why you should only stay briefly. And would you believe we've got 8 supervolcanoes in the middle of the North Island? So that's Taupo. And so it's quite dramatic. I've got, do I have 5 minutes left?
Yes, you do. Let you count down.
Oh, good. But what time do I finish?
0.
Ah. Right. I could go on and on. Because the middle of the North Island is subject to a rift, everyone, so it's being ripped open. So whereas here in Wellington, the Earth's being squashed, and what happens when you squash a sheet of corrugated cardboard, the ridges go up and the valleys go down. That's what's happening here in Wellington. In the middle of the North Island, we have a rift like that. And again, using GPS, we've determined that in Rotorua, up here, the east-west stretching is greater than 9 millimetres per year. And up in Tauranga, up on the coast here, it's 16 millimetres per year. So that explains why Auckland and Northland are sticking up at a funny angle off to the northwest. The North Island's ripping open like that. And the fulcrum is just south of this process, just south of Mount Ruapehu. There was a fault, the Edgecombe Fault, that moved in 1987, and it's part of this rift. It's on the east side of that rift. So it's located, let's see, in here, in this part of the world here. And there's White Island, and you might just see it in the distance, maybe not, but that's it in the distance, about 50 kilometres offshore, one of our 5 active volcanoes. And there you can see the fault snaking across the land, and quite spectacular offset on this road. And I just wanted to mention that in, let's see, 1886, that was our last volcanic eruption of basalt in New Zealand, and it came up Mount Tarawera, right here, along a fissure, 17 kilometres long. And this dealt to the pink and white terraces which were located around the edge of this lake. This is Lake Rotomahana. The interesting thing is that these domes of Mount Tarawera that formed in, let's see, 1312 AD, plus or minus 14 years, So basically liquid granite came up, but come 1886, what came up was basalt. So there you go, there's a rogue volcano. It's tapping quite different magma chambers at depth. And interestingly to me, is that this produced an ash back in 1312 that was quite widespread, and to my knowledge, no Maori artifact or occupation site has ever been found beneath it. And nor, to my knowledge, no iwi has any oral account of this volcanic eruption. So it's, at least, I would suggest for the northern part of the North Island, central to northern part, it's quite possible that there were literally no people living in that part of the world at that time. Here's Canterbury, another basalt volcano, Banks Peninsula, and there are the Southern Alps, a wonderful photograph. And I'll just point out that this is very different from the topography that we've seen in the North Island. Here we have, in this situation, continental crust versus continental crust. So this is analogous to what you see in the Southern Alps, in the European Alps and also the Himalayas. So I'd like to give you a quick analogy. Think of continental crust as cream and oceanic crust as milk. And when the two collide, you end up with quite different results. So where cream and milk collide, the milk flows under the cream, and that's subduction. And where you get cream versus cream, you end up like squashing two lumps of butter of equal density, and you get mountains forming in a big root, giving extra kick to the mountains, and so on. So in one small country, we have a bewildering array of landforms which relate to these three principal different types of crustal collision. In the north, cream versus milk. In the middle, cream versus cream. And in the south, milk versus cream. And here's a cartoon of what's going on, giving rise to the Southern Alps. Essentially, we've got granite on the Australian plate and Greywacke schist on the Pacific plate. And it turns out the Greywacke and the schist are, just think of them as big piles of ground up granite. And here we are in Milford Sound, back to, I know that probably the most different topography that you Australians will encounter in New Zealand is glacial topography. And here we are in Fjorden. This is an unusual view of Mitre Peak. Milford's just down there. And all this has been sculpted by ice over the last 2.5 million years, the ice ages. All right, so here are the conclusions very briefly. You've seen these already. But just think of it this way, that we are indeed the product of three phases of history: our Gondwana history, our Zealandia history, our New Zealand history. The New Zealand history is just the last 25 million. When Zealandia was pulled away from Gondwana, it was stretched and thinned and slowly sank. And it reached a low point about 23 million years ago. And me and a couple of others have dared suggest that perhaps there was no land at all back then. But we cannot prove that that were true. They may well have been islands. So I'll leave it at that. And that gives you 1 minute of questioning. So thank you very much.
Ladies and gentlemen, you actually have 10 minutes worth of questioning. The countdown was for the 30 minutes of the talk. Jess and Lisa, there are some roving... Oh, okay. Yeah, roving mics. I'm going to ask Hamish the first question, if I can. In Papua New Guinea a number of years ago, I was told that if a serious earthquake came, serious enough for you not to be able to stand, the way you were able to get out of danger was to roll. Is that the case?
Oh, that's... You won't have any opportunity to do anything other than roll. I have spoken to people here who have been experienced earthquakes, such as in Christchurch and Kaikoura, and if you're in the very high intensity shaking zone, you will be lying down. Yep.
Questions?
Yes. Oh. Of course, you've got to get the microphone from one.
Put your hand up so that they can
It's
find
on.
it.
Thank you very much for an excellent lecture. My question concerns more contemporary history. Could you explain to me what effect the melting of the glaciers had on the oceanic shelf? Did it, the mass of ice, did that cause the shelf to rise?
Yes, it did. So we would have, in that part of New Zealand, we had isostatic rebound, effectively. So there was literally kilometres of ice. So everyone, the height of the last ice age was between 18,000 and 20,000 years ago. And average surface temperature, this is what I was told many years ago, was about 5 degrees Celsius below present. That's not much. So Auckland would have had the climate of Invercargill, and sea level at the coldest point of that last ice age was 125 metres below present. So there was no Cook Strait, it was a gulf. There's relatively shallow water, especially at the western end of Cook Strait. So there would have been a continuous landmass embracing Stewart Island, South Island and North Island. And this has happened repeatedly in terms of the ice ages. So over the last 2.5 million years, there have been many ice ages. In the last 800,000, there have been about every 100,000 years. And prior to that, they were every 40,000. And average height of sea level over the last 2.5 million has actually been 65 metres below present. So the land has changed dramatically, and I would say in Wellinngton, there would have been alpine flora pretty much, almost at the height of what at sea level, at what is now sea level, would have been probably at the top of the bushline. Hard to get our heads around, but there's been. We look at our landscapes and we think, oh, they've always been this way, but they are, in fact, very dynamic. Wellington Harbour is only about 15 metres deep, and modern-day sea level reached its present height only 6,000 to 6,500 years ago. So if we were here 10,000 years ago, there wouldn't have been a harbour. There might have been a lake there. So it's a very dynamic process. And of course, when the ice goes, you get, because of the weight, the sheer weight of kilometres of ice on the landscape, it depresses the landscape. And then when the ice goes, you get isostatic rebound. It's not huge, but it's centimetres, measurable in centimetres to metres. And it's most graphically observed in Scandinavia today with respect to the ice effects in the northern hemisphere.
Keep your hand up.
Thank you. It's been fascinating. Do we know what causes the ice ages?
Do we know what causes the ice ages? Well, there is something called the Milankovitch effect, which is about cycles about every 40,000, and it's to do with the activity of the sun. And Earth's orbit doesn't change all that much. The only other factor that can influence how much solar energy arrives here is what lies between us and the sun. And that can be, you can get effects on this planet, huge volcanism. You can get meteorite impact that can create phenomenal dust effects. It's thought that 66 million years ago, with the meteorite that destroyed or caused the dinosaurs to go extinct, that dust effectively in the atmosphere caused complete absence of light reaching the surface of the planet for some months. So we've got our own atmosphere, and then, of course, material that lies between the sun and this planet. So we think we know, but what we are uncertain of are what were the triggers that changed. Why did it go from being interglacial to glacial? So those are still open questions, as I understand it. Mm.
Thank you, Hamish. With all those volcanic and earthquake alarm clocks ticking away, how do you ever sleep at night?
New Zealand is blessed. Our government has created a Ministry of Civil Defence and Emergency Management. And they hire some of the brightest minds on the planet, try to figure out what to do and when. Good luck to them. But we are getting much better at forecasting and figuring out the future. In 2011, you'll recall that very large earthquake off Japan. Colleagues of ours went to the Japanese government the day before the earthquake and said, look, we're very concerned. Our GPS data and seismology data and all our modeling tells us that there is a greater than 95% probability of a great earthquake occurring in the North Japan Trench within the next 10 years. And the earthquake struck the next day. So that's how bad we are, humanity, at figuring out when the next big event is. Or to put it another way, that's how good we are now. So we're a lot better than we were, and I think with supercomputers, we will in fact be able to pretty much predict earthquakes in the future, just by dint of having vast amounts of data and supercomputers. So I think there really is, things are looking brighter. I live on solid rock, halfway between two active faults, and it's much worse in Japan. Think of it that way. In Japan, the rate of plate collisions about 10 centimetres a year. Here it's only 5, so that's the governing number. The crust is trying to move at 5 centimetres a year, the rate that your hair and fingernails grow. Can I just make a final comment that it has been established that there are about 15 days a year when conditions are optimal for moving stuff from Australia to New Zealand. So tomorrow night, I'm going to have the opportunity to talk to you again, and I'm going to talk about things Australian in New Zealand.
Hamish, thank you so much. Nine of you lucky people in this room will have the pleasure of having Hamish on your dinner table. And he's a wonderful dinner companion. Hamish, I'm going to present you with a small token of our gratitude.